So I will be talking about the following problem. I will present a model that is useful in finance, in financial econometrics. And the idea is the following. I want to model a series of covariance matrices that they evolve across time. So I have data that they assume that they have zero mean, multivariate normal, and the covariance matrices capital sigma T evolve across time. And this is a usual application in financial econometrics where the data represent returns of some kind of assets. Now, why this problem is interesting? The problem is interesting for the following reason. First, the number of parameters in the covariance matrices are n times n plus 1 over 2. So we have a large number of parameters evolving across time. Second, these parameters have to obey the positive definite constraints of the covariance matrix. And there is a third problem, which I will mention sporadically in the talk, is that in reality, when you do analyze such kind of data, you have a lot of missing values. My focus will be first on the model, and second on the computational complexity that one meets if the number of parameters, if the number of assets is large. So for example, a typical application will be that someone would like to analyze, say, 4 years of data, which is about 1,000 time points. And maybe these applications are applicable in portfolio analysis, and the number of assets could be hundreds. Okay, so capital N, which is the number of assets, you can think of it as hundreds, and capital T, you can think of it as 1,000 or 2,000 if you want to analyze 8 years of data. So let me go straight to the model. First I will construct a model to solve the problem of the problem number 2, which is the one that the parameters have to obey the positive definite constraint. Now, I will take the matrix sigma T. I will use a spectral decomposition, and the spectral decomposition has a eigenvector matrix ut and eigenvalue matrix lambda t. And what I will do now is I will reparameterize the eigenvector matrix ut with respect to given rotations. Now let me tell you what given rotations are. So I write every eigenvector matrix ut as a product of n times n minus 1 over 2 rotation matrices, capital G. Right? Now, the eigenvector matrix has n times n minus 1 over 2 parameters. And there are also extra n parameters in the n eigenvalues. Now, for the people that are not familiar with this kind of reparameterization, the idea is the following. If this is a spectral decomposition in 2 dimensions, so I have 2 eigenvalues, and I also have another extra parameter, which is the rotation angle omega t. And this first matrix with cosines and sines is a rotation matrix. And if you want to think about 3 dimensions, I can write the eigenvector matrix as a product of 3 matrices and 3 rotation matrices. And these are the 3 rotation matrices. And each one of them has 1 parameter, and this is the rotation parameter. So in a sense, because the eigenvector matrix is a rotation matrix, I can write it as a product of smaller rotation matrices, and each one has a rotation in a particular plane, and this is specified by a rotation angle, which are these omega angles. Now, the reason I'm doing this is because now the parameters of the eigenvector matrix correspond to rotation angles, right? Now, the very big formula, the one that I will be using, has the following form. So I have an eigenvector matrix capital U. This has n times n minus 1 over 2 parameters, right? And I write this as a product of n times n minus 1 over 2 rotation matrices of this form. And these matrices have a nice sparse specification. So if you can view it, there are only 4. The diagonals are 1, and there are only 4 elements that they are non-zero. Okay, and I will be using this later when I discuss computational complexity. Okay, so what I have done now is I have converted the elements of the eigenvector matrix to rotation angles, right? For every element in U, there is a rotation angle omega. Okay. And now I can write down a model which at least evolves across time and although it does not evolve in the manifold of positive definite matrices, it evolves in R to the power of n times n plus 1 over 2, I can transform it back to a positive definite matrices. So for every eigenvalue, actually logarithm of eigenvalue, and every logit of rotation angles, I can impose an autoregressive one process. Okay, so this is a process that involves across time, and then for every time t, I can convert back to positive definite matrices sigma. So in a sense, I have not solved a big problem now. I have solved problem number one, which says try to write a model that evolves across time and corresponds to a positive definite matrix sigma. Now, so these are n times n plus 1 over 2 autoregressive processes of order 1. Okay? So I converted the problem is not easier, but at least I can write it down. Now, since I'm Bayesian, I have a series of autoregressive one processes. These are all latent processes because my observed data are returns, and these are covariance matrices. Maybe I would like to impose some kind of structure on the prior, and the natural but not necessarily important prior structure is to assume some kind of exchangeability between the parameters of every autoregressive one process. Okay, this is not necessary. I do it because of my culture to start to thinking a little bit about hierarchical models and shrinkage. And these are priors of the parameters of each autoregressive process, that they borrow strength between each other. So, okay, this is my model formulation. And of course, I can extend it. I can extend all the factor models using this kind of formulation. So the usual factor models in financial econometrics, and I think in other applications, is that you can have a factor loadings matrix B, and you can reduce the dimensionality of R using a factors F, which have smaller dimension. Now, usually, the correlation in R is imposed through B. So it's static. It only depends on how f of t varies, and f of t usually are considered to be independent. If I use my previous multivariate stochastic volatility model formulation, I can extend this to this model where f, the factors, follow a multivariate stochastic volatility. So they are correlated. So the actual correlation in RT comes not only through B, capital B, the factor loadings, but also through correlations of f of t. And in somehow I can think that this is plausible, because if your factors are not unobservable and you do proper financial analysis and you pick up some factors, these factors usually are correlated. So it makes sense to think that even the unobservable factors are correlated. And the second, when I write down this model, still the complexity is amazing, right? Because n, capital N, if you think that capital N is 20, you have 20 times 21 over 2, 210 parameters, and that evolve across time, okay? So when I try to design well, I use an MCMC algorithm here, but whatever I do, I have to be very careful about the scalability of this algorithm. Now, one problem here is the following, that every time, whatever I do, whatever method I use, I have to calculate the multivariate normal density. And calculation of the multivariate normal density is O d cube, where d is the dimension of the density. Okay, this is the usual problem in Gaussian processes and other applications. So what I'm going to present here is, because I use this kind of parameterization, I can do all these calculations in quadratic complexity rather than cubic complexity. That's one thing. And there are other things that I I will discuss throughout this. So let me go through that. Assume that I want to do an MCMC algorithm, and I assume that I will be using this model. So this is the more general model. F of t are the multivariate stochastic volatility latent paths, right? So f of t follows a multivariate stochastic volatility. Sigma t vary in the way I just described, right? And B is a factor loadings matrix. And if I wanted to do an MCMC, in summary, I would sample from these three I will have these three steps. The first step is to sample beta, sigma square, and the factors. And the last part is the third part is to sample the parameters of autoregressive processes. Now, the very first and the very last part seem to be straightforward, right? These are normal densities, conjugate Gibbs, blah, blah, blah. This is not interesting. The interesting part, of course, is the second part. Now, with capital X here, I have all the latent paths. So capital X denotes all the rotation angles and eigenvalues across time. So just to give you an idea, in my application that I will describe later with 30 factors, 2,000 days, the dimension of this capital X is 1 million, around 1 million. So I want to sample this vector of 1 million. And in a sense, this problem is a usual Gaussian latent variable problem that people have tried for a long time to find ways to do either interesting Metropolis casting algorithms, or if the dimension is smaller, you can think of nested Laplace approximations or many other approximations. So let me go directly and discuss the number 2, the probability of the latent path given the rest. Right? How do I sample from this? Of course, the very initial univariate stochastic volatility model says sample each element separately. Sample x1, x2, x3, x4, etc. Of course, this will never work here, right? The MCMC will never converge. Now, I will propose an algorithm that samples all this vector of x at the same time. Okay, so it's a kind of Metropolis algorithm. It's not exactly Metropolis, but I will propose I will do a Metropolis casting in this huge dimension with the following way. Now, the intuition is the following. I want to make a move which takes into account two different parts. One is the prior structure, which is an autoregressive structure, is the structure I imposed through my autoregressive one process. And also, at the same time, I want to take into account the likelihood. Right? Depending on the noise to signal ratio, et cetera, maybe I want to do one more than the other. But if I don't take both of them into account, my Metropolis will never work. Right? So one idea is the following. It's based on a discussion by the third co-author in a paper of Girolami on Hamiltonian dynamics. And the idea is the following. So I want to sample X and assume that I want to do a slice Gibbs. How I will do a slice Gibbs? I would introduce an auxiliary variable, and I will sample, and I call this here U, and I will sample U given X and then X given U, right? So let me introduce U first. U is an auxiliary variable, and the way I introduce it is I sample from something that looks like a Langevin. It's not exactly a Langevin proposal. It looks like a Langevin. But the interesting thing to look at is that my U will use the information in the likelihood. So it will move slightly towards the direction that the derivative of the likelihood will tell me. So I'm at time n at position x, and I will move in the direction in all big space of the likelihood. And this is my U. Then I want to sample x given U, but I cannot. So what I will do now in my slice Gibbs, I will do a Metropolis step. So I introduce the latent variable, and then I do a Metropolis step. And when I do a Metropolis step, I need a proposal, and this is my proposal. And the proposal has the following interesting product. It's a product of, this is a normalizing constant, so you may forget about this. This is the prior, so it takes into account the structure of the autoregressive process in this 1 million dimensions, if you want, times something around the proposal U, which already has information in the likelihood. So you see, it takes into account information on the likelihood and on the prior. Okay, the prior is very important in this case, right? Because it's huge. Now, the other interesting thing, and I will go through, I will not go through the calculations, is that when you do the acceptance-rejection ratio, you end up to something like this, which has the ratio of the two likelihoods, but does not have the prior. So the prior has disappeared. So this proposal is invariant to the prior. Okay, and for when you do the calculations, you will see that this is very important, because this prior is a prior on 1 million dimension. In 1 million dimensions, you run your MCMC, you have every time to call it and do the calculations. Although it's not very expensive, still it makes a lot of sense to use an invariant to the prior proposal. Okay, there is a delta in this algorithm, and this is something that we tune. And this is the usual tuning parameter in the Metropolis or Langevin algorithms. Okay, now why? This is the Metropolis step. But in this Metropolis step, I need to calculate the likelihood. And the likelihood is a multivariate normal. So the next problem is this multivariate normal requires a lot, has a cubic complexity. So I must find a way to do it faster. And actually, if I exploit this way I wrote down my sigma, my covariance matrix, I can do it in quadratic complexity. And let me tell you the idea. So this is how I write down the log density of the multivariate normal, okay? And the last part, which is the interesting part, I wrote it as Vt transpose Vt, and Vt is this matrix. So what I have done is I took this part, the usual multivariate likelihood part, and if I look at it carefully, the only thing I need to calculate is this vector, because it is, of course, multivariate normal density is a scaled vector rotated. So this u rotates my data, and this lambda scales the data. So if I manage to calculate this, I'm done. Okay, why this is, I can calculate this faster now? Well, I can calculate it faster because this u is a product of rotation matrices. So this requires n times n plus 1 over 2 multiplications, right? Someone might think that now if I want to calculate u, it will take me a lot of time. But actually it will not, because u is a product of G rotation matrices. So I cannot describe it here, but I can describe it with my hands, being Greek. So I have a series of rotation matrices times a vector, and I want to do this multiplication. So the first thing I have to do is the last rotation matrix times a vector. But the last rotation matrix has only 4 elements which are not 0. So when I multiply this rotation matrix times a vector, the only thing to do is I change 2 elements of this vector, because I only rotate it on that plane. Okay, so this is O1. And then I have a new vector, and then I multiply with another rotation matrix, which is again O1. So all this calculation is very fast. I just don't multiply, I just replace elements. And this is the idea, and the same idea I can apply to do the derivatives for the Langevin, et cetera, et cetera. So I can do all these calculations in quadratic complexity. When I presented this algorithm, I said in a rather clever way that the first one and the last one is easy. This is the first step, which is the conjugate step, and this is the last step, which is, again, a conjugate step. But when we started running this algorithm, we noticed that we don't get a lot of computational improvements. And the reason we don't is that although this is when you sample the factors f is conjugate, in the good old days when something is conjugate, you sample from a normal distribution and you are done. Here, this normal distribution requires to do some calculations. Okay, so what is this f? So when you try to find the density of f, you need to do some calculations to find the covariance matrix M. And this requires to find sigma. And to make the long story short, this has cubic complexity. So sampling with GIP sampling for IID samples from a normal density seems to give me a hard time. So instead, what we did is, instead of sampling directly from a normal density, because it takes a lot of time to calculate the covariance matrix, we sampled again with a Metropolis. So we replaced the nice IID sample with a dependent sample. Okay, and this reduced the complexity to T and K. Okay, so we saved a lot of time even on this simple IID thing. And 2 or 3 graphs to show you how well we do. So what is this graph? I took one way to compare these models to see how well they predict. Okay, so how do we test that? We have our in sample, we stop, and then we say, let's see what happens in the next 100 days. Can we predict well? Okay, so one way to predict, one way to test that in Bayesian statistics is to calculate the predictive Bayesian factor, which is in every day you calculate the log posterior, the observed log posterior, you multiply, and then you calculate the log marginal likelihood. So the top graph, so this is log marginal likelihood, so even a difference of 5 or 10 is huge, right? The base factor is e to the power of the log marginal likelihood. So the top two are our multivariate factor model with the 2 different priors you used. The exchangeable prior, which does better, is the red one, and the blue is the prior, the independent prior. The other one, the black one, is something that the referee insisted that we should compare with, is the independent factor model. Okay, and the independent factor model does well with 2 factors, and then everything is noise. And then if you go up to 29 factors, it performs really poorly. Okay, so in terms of predictive ability, it's worth using a multivariate factor model rather than independent factor model. In terms of computational complexity, this is what we achieve with the Metropolis instead of the Gibbs step. So although someone might think that, Metropolis probably makes and actually the effective sample size is even better. So in every respect, we win. So this is the average computing time in seconds, and as the number of factors increases, the Gibbs sampler goes up here, and this is the ratio, which is about, with 20 factors is about 10. Okay, so this is a small proof that someone made us to do. And then in the big problem I described before, I forgot to mention, because I'm going very fast, I forgot to mention that the missing values is not a problem when you sample factors. Because the traditional way is to impute the missing data in the returns. But if you impute, you have to calculate all these normal densities in high dimensions, and this again is very costly. But if you sample factors, you are okay. And then this is a big example we did, which is 2,000 days, 600 stocks from the European Stock Index, about 1 million latent, a dimension of the path is about 1 million. And this is my tablecloth, which is the only way I thought to present the data. And the data is the following. Here is the time, which is the 8 years. And here are all the pairwise correlations, right? And since I have 600 stocks, these are 600 square over 2, whatever, correlations. So these are all the correlations across time in the past. And the interesting thing is that there are days where, and these are all 600 European stocks, or major stocks in Europe. And these are different cases in Europe. We went back and we traced, as biologists do, to see whether we have something rubbish here. And these are all days where things happened in Europe. And this is the Libor scandal in the UK, et cetera, and these are crisis days and stuff. So we pick up days dynamically, days where all the correlation increases in all stocks. Okay, and I think I'm just on time. How I managed to do this in 20 minutes, I don't know. What I presented today is a model for modeling covariance matrices across time. A new MCMC algorithm which is applicable to Gaussian latent variable models, where you can sample all the latent path at the same time and take into account information from both the likelihood and the prior. And I think we were extremely careful on how to deal with computational complexity, so the model is not used for something which is not applicable in finance, but it can be used to to a series of, to many stocks. Thank you very much.
Sophia invited me to give this talk. I have to admit I'm a complete imposter in this environment. I have no statistical background and expertise. But what I was, as Sophia says, what I want to do is give an introduction to topological data analysis and maybe make your appetite, whet your appetite for this area. Okay. Our interaction. Is that better? Okay, good. Let's see what I can work this. Okay. So what is topological data analysis? Well, in a nutshell, in a slogan really, the idea is that data has shape, and shape matters. So when you have data and analyze it, you shouldn't ignore shape. That's basically the idea. But of course, shape is difficult to quantize, and you might wonder how easy will it be to incorporate it into your analysis. And hopefully I can convince you that it is not too difficult. So what is topological data analysis? It's really a new way of looking at data. And there's one particular tool that is most common, that's persistent homology. And that's the one I like to concentrate on. And, well, this is not actually me saying it, but people from outside have said it. Possibly it's the only method catching really global information of the whole data set in a way. Okay, so what is shape? What do I understand about shape? I'm a topologist, so one simple example here is a donut. The shape of a donut, its topology is actually very simply encoded in having two different cycles. So there's a purple one and a red one, so they're one-dimensional cycles. You can think of other ones, but we'll see later that really, I mean, you can think of a spiral going around, but really that we can realize as a combination of those. And then, of course, there's another thing. There's another hole here, namely the void. So when I'm talking about a torus, I'm not thinking about a donut, but it's hollow. So it's more like an inner tube, or the surface of a donut. So really the void, the cavity inside, is a very important topological feature. So the torus having two one-dimensional cycles and a two-dimensional void, and of course being connected, that completely describes this torus as a topological surface. And that's a very important characteristic, because you might wonder, well, what would happen if I look at a ball, a sphere? And of course, the sphere also has a void, but it would not have any of these cycles, because if you have a cycle like the red one or the purple one on a sphere, and think of it as a rubber band, it of course completely contracts. So these sort of statistics completely describe surfaces for us. All right. So if I start now with data, then I want to describe somehow, associate somehow to it a shape, a topology. Starting off with point clouds for the moment. One can do all sorts of other things, but let's think about a point cloud. And of course, a priori, it doesn't have any shape at all. It's all discrete points, nothing there to tell us, apart from maybe distances. And the distances are important, but not just one distance to another point, but potentially how 3 points interact. And if you I guess this is the picture here. I have drawn an epsilon ball around each of these points, and now I get some shape here that I might think of representing the shape of the point cloud. Now, this is important for later here. What shape this is, of course, depends very heavily on the epsilon I choose. And indeed, in a moment, I will have to think about taking a choice for all epsilon at the same time. But let's keep that for a later slide. Right now, I'm just having one epsilon, and I consider all these balls, and the union of these balls give me a shape that I can think of representing this point cloud, data point cloud. Okay, so from that, and it's already indicated here, I can construct certain complexes. So let me do that. That's next, right? So I want to build up something combinatorial, right? Because combinatorial things are much easier to analyze than something that is of this shape. How would I describe it in an efficient way? The combinatorial data here is really the complex. And there are various ways of doing it, and there are certain advantages and disadvantages. I won't go into it. But let me just start with a very simple one. This one here. I have, this is the so-called check complex. Whenever 2 points are within epsilon reach and their balls intersect, I put an edge. Not simple. On the other hand, if I have actually 3 of them intersecting at the same time, then I put not just the edges, but also a triangle. And similar, if I have 4, I fill in the triangles that I have for all subsets of 3 with the solid simplex, and so on. So I built up a complex here. A complex is, in other words, I can describe as a sequence of points, the vertices, a sequence of edges, namely one edge for every 2 points that are in epsilon distance, given this epsilon, and triangles whenever I have 3 that are within epsilon reach of each other. So here's the way I now recover the cycles that I mentioned earlier in the torus formally from the simplex or complex as I've given. It's pure linear algebra. In a way, it's much simpler than what we've seen before in the previous lecture. So what I want to do is I take the vertices here. I take a free, I think of it as a basis of a vector space. I take the edges, and again, they form a basis of another vector space, and so on. And here the n-dimensional, the n simplices, the number of n simplices, and I take a vector space on that free vector space. Now, they come actually connected by what I call a boundary map. And this boundary map is actually very simple to define. I wish I had a marker, but I don't. So given, let's start with this. Given an edge has 2 endpoints, and there are 2 vertices associated to it. So I can just simply take one edge and send it to the sum of the vertices underlying. Okay? So let me go back. For example, this edge here, this is a basis element in for K2. I have this and plus this element as its boundary. Okay, very simple. So I guess I have taken my vector space to be just simply plus and minus 1, but I can make it more fancy, and as long as I then take the signs into account, that will work. But the idea here is now, given an element in any of these kns, I just simply associate to the simplex, to the n simplex, all the faces, the n-1 faces, and sum them up, possibly with sign if I'm in a more complicated field. And then here's the key observation, namely, if I take the boundary of a boundary, so two of these maps, one after the other, then I get actually 0. And this allows me now to consider the homology. The homology is the kernel, everything that goes to the 0 of dk plus divided out by the image of the previous map. And if you just want a numerical invariant, this is the Betti number, which is the dimension of this homology group. But I can also just think of it as the dimension of the kernel minus the dimension of the image. Now, as an example, let's look actually at the torus. What is a torus? Well, the 0 Betti number, which just tells me how many connected components there are, will be just 1. The first Betti number will tell me how many cycles I have, 1 cycles, and that will be 2. So the dimension of the space of 1 cycles will be 2. And the second Betti number will be 1 again, because there's just basically 1 void in the whole thing. In comparison, for the sphere, you would have the 0 Betti number to be 1. Of course, there's 1 connected component. Then no 1 cycle, so the first Betti number will be 0, and there's just 1 void, which gives you a second Betti number equal to 1. So that's very basic topology. But now we need to do something about this idea that we picked an epsilon. And it's not clear a priori when you have a set of data what epsilon, what choice of epsilon will give you the right sort of idea. I mean, here you might think, oh, there seems to be a circle here and maybe another circle here, but nothing interesting happening here. And that's reflected here. There's a little hole I can see, and possibly there's a little hole here if I chose the epsilon correctly. But of course, if I choose a very large epsilon, then this just becomes one big block and nothing interesting is happening. So that is something that needs to be taken into account. And so as we vary this epsilon, as we let these balls grow from something very small to bigger and bigger and bigger, we get actually complexes which are nested. And so here we have an example which you can think of a complex for varying epsilon with different vertices getting connected and higher and higher. So, with this here, it's clear that I have 3 different connected components. So B0 is 3, while B1, there's no cycle, so that's 0. Here I have 1 cycle. Here I have actually 2 cycles. So the 1 cycle I had here gets filled in. And finally, I just have 1 cycle, and so on. Yeah? Then we now look at how these different cycles fit together in order to get a statistics, the so-called barcode. So in dimension 0, so if we follow B0, then, okay, we start off with 3 different connected components. Those 3 continue at the second step to, well, basically this continues, but I get 3 new ones, and finally I get, in dimension 1, I just realized that's a mistake here, never mind. Let's look at dimension 1, I have no 1 cycle here, I have 1 cycle there. That gets killed, there's no 1 cycle, this is just a blob. That gets killed at step 3, but I have 2 new ones at step 3, and one of them gets filled in step 4, and so on. So with these codes, I can actually see not just how many of these cycles I have, but also how they fit together, how they, at different times for different epsilon, continue to persist. And so the idea is if I have something that has a long bar here, like this one here, this will now persist forever, and that's going to be significant, while short bars should be something less significant. Okay. The statistical analysis and interpretation of the results is not an obvious area of study. Namely, we may want to compare, of course, different expected might want to compare our analysis or outcome with the expected or unhealthy outcome. Or we might want to take averages over different computations for different epsilons, for different variations of our data. And so one can proceed by defining metrics on these spaces of barcodes that I just given you as our statistical summary, namely, here. Right? These are our statistical summaries, these barcodes. So we have a metric on them. We can also map these barcodes into a Banach space, in a suitable Banach space, and try to analyze things there. One of the most important, it's actually a theorem that you can give these barcodes. They're well-defined, and it makes sense. That's one of them. But the other one is stability. Namely, with a small perturbation of your data set, you only get a small perturbation of your statistics, namely of the barcodes themselves. So these stabilities give us confidence that indeed you can try to analyze data this way. Okay. Applications. There are many applications, and I don't have time, but maybe the most important known and well-known one is the top one. Topology-based data analysis identifies a subgroup of breast cancer. And indeed, this is a study where they used TDA to understand, to pick out a certain breast cancer which has 100% survival chance, and which, of course, is fantastic if you need to treat breast cancer. The next one I just put up is my colleagues in Oxford have studied, used topological data analysis in contagions on networks. And a very interesting, very new study is the third one, where they have looked at nanomaterials in particular. They have tried to figure out which silicon and oxygen combinations, molecule structures are good for catching carbon monoxide. And from my perspective, what's interesting, they're not only have they used sort of connected components, the B0, but also they have used actually voids. The second Betty number comes in the analysis. And another application here to computer vision. Okay. Many software packages do exist. So there has been computational packages. I put down our paper here, which is really a roadmap if you want to start computing topological TDA and persistent homology of your data. But I also put down these other papers here, which might be interesting to a statistics audience, because they are actually about trying to analyze not just the barcodes. It's the statistical packages here that have been developed. Challenges. The TDA challenges are manifold. It's a very new theory, and but with the challenges come, of course, the opportunities. The pipeline that I haven't really emphasized, you first have to associate a complex to your data, then you have to calculate your homology, and then you have to interpret your results. Well, in particular, the calculation of the homology, though everything is linear algebra, it needs to be sped up. We can do relatively large samples, but not something that you might want to call big data. Bridging the gap between user and developer, I think that's a very important one, because though everybody understands connected components and maybe cycles, I think voids and three-dimensional homology, four-dimensional, we can go into any dimension if you like. Those sort of topological intuitions, I think, are not so easy to grasp from somebody who wants to apply these things. Another thing is we want to not just have maybe the epsilon grow, but possibly the importance of certain data points. So we need to develop multi-parameter persistent homology. That's one thing I'm interested in. And finally, there are just many theoretical underpinnings that need to be sorted out and better understood. This is something that can go under the slogan of manifold or space learning. Okay, conclusion. I think TDA is a new interesting point of view to look at data. It's combinatorial and hence actually quite easy to grasp or to compute. It has a degree of robustness, namely that can be quantified, namely the stability that I mentioned earlier. And it has been applied to many domains. And so let me just finish where I started, namely with the slogan really that data has shape and shape does matter. Okay, thank you.
So what I'm going to talk about is the latest results we've been of the type of models we've been working on with Peter Green. Which has been extended recently to ill-posed and misspecified models. So I'll start with the introduction to the problem, and then I'll talk about the go briefly through the result for the well-posed likelihood, and then the extension to the ill-posed likelihood. And the well-posed case also include possible model misspecification, and then I illustrate on the motivating example that we had, and I conclude with the discussion. So just to set the notation, so for the ill-posed case, I assume that the likelihood depends on the parameter only via some linear combination, so matrix A is given. In the well-posed case, it could be sort of the n transpose A is a full rank. In the ill-posed case, it's not. And then look at the Bayesian model, so some prior distribution density, sort of P is generic notation for a density, and then, of course, one can construct various decision rules. So this is the motivating example, which I think Peter and I started looking at it years ago, and it seemed to be such a rich problem. We're still finishing the work. So it's a tomography problem, so there are indirect observations. So towards the exposure time, and yi is the frequency of observations in this time. So the overall number is Poisson with, which is proportional to the sort of, again, exposure time. A is radon transform, theta is the unknown. In a sense, you can think of it as an image that generated this data. So there is a constraint that elements of theta are non-negative. So we can look at the moment. So of course, so that is the inverse problem here, and the variance is proportional to that and also inversely proportional to the exposure time. So naturally will go in the limit when the exposure time goes to infinity. And the aim is to recover the unknown image, and the prior distribution that Peter used is the non-Gaussian pairwise interaction Markov random field. So you can see that actually this prior is improper because it's not identifiable for theta up to a shift, right? So you can add and subtract. So this is, the sum is over the neighbors on the image. So, and the asymptotic, as I mentioned, is the exposure time going to infinity. That is, in this case, the variance level going to 0. And the non-standard aspects are that we have the constraints. We have possibility of Poisson mean 0 in principle, so we can have degeneration. A can be ill-posed, and the prior distribution is improper, right? So what we wanted to look at is sort of the asymptotics, how the corresponding posterior distribution concentrates around the map, perhaps estimator, or sort of from the frequentist perspective, possibly about the true value of the parameter. So another one, sort of just a toy example to give you maybe with a few pictures. So suppose we have a linear ill-posed problem, sort of Gaussian errors and Gaussian prior, sort of really a bit trivial example. And then, so effectively, any solution on the line in the limit of θ1 plus θ2 equal to 1 is a solution. And choosing the prior actually determines which solution on the line that you use. And say we have Gaussian observations, and when we plotted the posterior distribution and the contours, so this is what we were getting. So this is sort of medium sigma. Then when we were decreasing sigma, these were the type of shape we were getting. This is sort of recentering and rescaling. We just swapped the axis, I think. And these are the densities along the y-axis. So the standard result, I'll show it formally in a moment, is that if the model is regular, the posterior distribution should be Gaussian, right? So you can see that it's certainly here, it is not Gaussian, even though we have both likelihood and the prior Gaussian in this case. Just to talk through the setting, I assume the finite dimensional setting, but the possibility that the number of the dimension increase. It's asymptotic framework, but we have non-asymptotic upper bound on the approximation on the between the posterior and its limit. There are non-regular aspects, including constrained parameter space and degeneration of the likelihood. Also, we allow the model to be misspecified. The results hold for a misspecified model. And we consider effectively, through the ill-posedness, we consider a non-identifiable model. And we study the local concentration of the posterior distribution around, for well-posed models, around the true value of the parameter, for the misspecified models, for the best approximation in the considered model space. So this is formal formulation of the Berstein-von Mises theorem for regular models. Effectively, if the likelihood is regular, sort of just open space, identifiable likelihood, smooth, finite Fisher information. The prior here, I haven't said, but assumed to be proper with continuous density, at least in the neighborhood of, for the well-specified model, theta star. And then if you recenter the theta by theta star and renormalize by root n, then asymptotically it's normal distribution with some random bias, and the variance inversely proportional to the Fisher information. That holds sort of in total variation norm. And that allows to construct asymptotic credible intervals showing the Bayesian inference is efficient, right? So that is the efficiency bounds. And, however, for misspecified models, instead of the Fisher information here, it's replaced by the minus expected value of the second derivative of the log likelihood. And then we actually lose the efficiency. And in fact, there is a work, I'm not going to talk about it, but what is the efficiency bound on of the misspecified models, and how to achieve that in recent work by Niall Friel and his PhD student. Okay, just to say this is a formulation for ID models, but in fact, there is a more general model, sort of local asymptotically normal model introduced by Lecam, for which this holds as well. So, however, our model doesn't satisfy these assumptions. We have, it's not an open set. We can have a parameter on the boundary. And in fact, the prior is not proper. Right, so I'll just go quickly through the well-posed case just to explain what happens, and then I'll talk about the ill-posed case. So the general assumption of the model is that the likelihood can be written this way, with a sigma being related to the noise level. That is, when we take the limit of this sort of scaled log likelihood, then we have the limiting function, which is deterministic, and we denote theta star the maximum of that, and we assume that it's unique. So if the model is well specified, then theta star is the true value of the parameter. So just to say that here we assume that P star, which may depend on sigma, is the true probability measure of Y, which may or may not belong to this class of models. So the limit is taken with respect to that probability measure. And there are various sort of places where this limiting function appears for in various settings. So just a simple illustration for the IID model. So here the limit is effectively constant minus the Kullback-Leibler between the true distribution and the model space. And again, there is interpretation for other cases for HMMs, and I think that's exactly the definition Spokojny uses in his non-parametric setting. And then also this works for exponential family with dispersion parameter, which dispersion sigma squared. And then in this case, this corresponds sort of to the Poisson setting I introduced in the beginning. And here the variance is proportional to sigma squared. So if we take sigma going to 0, we have this limit. So effectively, the log likelihood converges to the value to the log likelihood at the true sort of noise-free data. It's called an inverse problem. Oops. And that actually works for generalized linear models if A transpose A is a full rank 2. Okay, so this actually assumption holds for misspecified models where the likelihood is normal. But suppose we have a constraint, and this constraint is misspecified, for instance. We assume that it's, so for one-dimensional sort of parameter, it's a bit trivial, but you can think of that as you have a linear model and you're missing one covariate. Your covariates are positive or non-negative. For the parameters, also non-negative, but you're missing some components, and you might get similar situation. I think we'll have example in the paper for that. But just for simplicity, even in this setting, you can see that actually the limit is of this type, and the maximum is on the boundary. So if the true value is negative. Right. So then we assume this prior distribution, and this is the posterior density. So the prior may be improper, and actually for the classical Berstein-von Mises theorem, the density is assumed to be continuous and bounded away from 0 and infinity. We don't make assumption for that. So for instance, we allow for gamma densities or betas which can go to infinity around 0. So just the idea of the local sort of Gaussian approximation is when the maximum is an interior point, then the first derivative is 0, so the leading term is the second one, and so once you do the correct rescaling, you get Gaussian distribution in the limit, right? So, however, if you don't have that, let me just go back briefly. If you have what's called a sharp maximum, then the linear term can matter, right? So if we introduce the sort of different coordinates, so in the first case where derivative is non-zero, and then in the two cases where derivative is 0, and we consider also separately the case where theta star is also on the boundary, but the derivative is 0, so this there's bar without their star is the standard Berstein-von Mises cases we see, but in these two cases, the posterior distribution will be different. I'll just skip through. So this is the S coordinates effectively is where we have a linear term that is leading. So the rescaling is going to be by sigma squared, which will determine the rate, right? The rate will be faster. And then this will converge to 0, and for the remaining coordinates, the leading term will be quadratic, so that'll be Gaussian limit of the posterior. So if we do the change of variables corresponding to sort of the standard sigma for the internal ones and sigma squared on the boundary, then this is sort of these first two, just the standard parameters of the Gaussian approximation, and these ones are the non-zero values of the derivatives. Then we have that the posterior distribution factorizes sort of for normal, possibly truncated, where we have positive derivative, zero derivative on the boundary here, but where we have sharp maximum, the non-zero derivative, we can actually get gamma distribution. So this comes from the likelihood, and the shape parameter comes from the phi on the boundary. So if your phi is flat, then alpha is just 1, so that's exponential. But in principle, if you choose different distribution, phi can affect the limit of the posterior, and then we have that convergence of the posterior to this limit in the total variation distance. Right, so that's, well, the assumptions, I skipped that. So in the yield-post case, we also have the additional problem, so we have the part of the model that is non-identifiable. So the construction I told you, or the approximation rather, holds on the identifiable part, but what happens on the non-identifiable part? Let's have a look. So we have sort of generally the following framework, which we call generalized linear inverse problems. So effectively, we have the likelihood of the form that I assumed before, just but for parameter which is the mean of the observations, and then we have some covariates, or maybe in the inverse problems is linear operator A, and some link function, which can be any one-to-one function. And then we have a Bayesian model. We assume some prior density, just scaling gamma by gamma squared. So in principle, if you have an inverse problems and you look at the frequentist optimality of such inverse problem, you know that you need to regularize with parameters that depends on the number of observations so that you achieve the right result. So in principle, we have finite dimensional setting, but which can be used sort of as an approximation of that case. So in practice, for such inverse problems, the optimal value of the parameter gamma here will depend on the sample size, or in this setting on sigma squared, which can be thought of as 1 over n. And I won't sort of link it exactly to the inverse problem setting, but our conditions on parameter gamma squared exactly coincide with those necessary for frequency consistency in inverse problems. So in particular, we assume that gamma goes to 0 as well, but slower than sigma squared. Right, so this is just, the first line is pretty much repetition what happened before, except just to emphasize there is dependence on A, the linear matrix. So however, we have the part which is a non-identifiable part of the parameter, which is, so PAT is just the projection on the image of A transpose. And so effectively, if we add to theta minus theta star anything in the null space of A, then the expression doesn't change, right? So effectively, this is looking at the expressions of the null space of A. And here we use the decomposition effectively of the log of the prior distribution, which would affect the posterior inference on that part of the parameter space. And this is just Taylor expansion. Again, there could be a first-order leading term if the derivative of the prior is non-zero, and otherwise the second term will be leading to the Gaussian prior. This sort of here for the Berstein-von Mises-Taub result, we actually need a stronger assumption than just sigma over gamma going to 0, which are these error terms. But also, so this is the bias term, so we need to have sigma over gamma squared at least being bounded, or preferably going to 0 too. Right, so in these cases, you see instead of just the two spaces we had before, so AV being non-zero is the identifiable part of the parameter space, but we could also have the non-identifiable part. So that's W1 and W3. And then we also, each of them divide whether the gradient, effectively the leading term is 0 or non-zero, right? And then we have corresponding dimension. And the scaling, so we have sigma and gamma, effectively if the gradients are 0, and if they're non-zero, it's sigma squared and gamma squared. Right, so that's, so now we're getting 4 spaces, and matrix V here effectively determines the separation between the 4 spaces, which can be quite challenging, actually, in some cases. And then D is just normalization, and then we have the limit of the posterior distribution is just normal in the sort of product of normals and exponential, assuming flat prior. If it's not flat, then you can get gamma distribution here. I didn't want to introduce two more parameters. And then we have, again, convergence in the total variation norm of the posterior. And so this is just the going through the assumptions. So the interesting part that I personally found here is the combination of constraint on the parameter space and can actually lead to the null space to correct a solution of the ill-posed inverse problem. So for instance, this is sort of a simplified two-dimensional example, but you can imagine a multi-dimensional case with these two types of covariates. So again, we have just a simple matrix 1 and 1, but now we have effectively x star, so theta star is equal to 0, so the true observation is 0. And in this case, because of the constraint, actually the only solution lying on the line theta 1 plus theta 2 is equal to 0 is the true solution, 0. And the posterior distribution, sort of in the limit, what it tells us, there are two types of behavior. One is effectively that theta 1 plus theta 2 over sigma squared is exponential. That's non-regular behavior, but determined by the likelihood. And also where we have the null space, theta 1 plus theta 2 equals to 0, it just becomes a point, and there is a degeneration to the point mass at 0 in the space. So that's an interesting feature. Oops. So this is just an illustration how this works on the original spec model. So the gradient here, at least determined by the log likelihood in the limit, is just sum over those observations which have value 0 of the, I think, is it transpose columns of A. I think so. If it is non-zero, then we have exponential limit, and otherwise, if it's 0, it could be either normal or truncated normal. And so we do the comparison with the approximation, sort of robust approximations from the MCMC output. So let me show you. Right. So this is the original sort of reconstruction of the image, and there are 9 points, I think, taken here at some point. Well, actually, there are just 2 points taken here. So this is marginal distribution of one, and this is marginal distribution of the other. So you see, we get both normal and exponential type distribution here, and that's without going to the limit. That's just observed value, and these are the joint marginals. So you can see we can get Gaussian distribution, but also a mixture of Gaussian and exponential. Right. So just in practice, of course, we assume that this regular Berstein-von theorem will hold. But it is interesting to see that when you do inference about the boundary, particularly about hot or cold spots, we can have a more precise sort of approximation because it's actually of the rate sigma squared, which is faster than sigma, so it'll be more accurate. And also, all this framework works for misspecified models. So one way to deal with that is, for instance, if you have when the models are very complex, so here the number of the p-words, I think of what are think 64, something like 64 squared, I think. But if the model is much larger and one might want to do simplifications, then one way of dealing with it is suggested by Niall Friel, for instance, run a simpler model and then adjust for the covariance matrix using just a linear transformation so that you get the correct covariance matrix you'd expect, at least in the Berstein-von Mises theorem regular case, and also you can do it in the non-regular case using our result. And this is sort of what I was thinking about, that I think it's coming up in machine learning papers that say you are given fixed running time and you have exact model, but you cannot run your MCMC up to maybe as long as you want, so you still get possibly larger MCMC error, or you can run an approximate model which is much faster, so you get additional approximation error. And so one could actually use this to construct a formal framework, given computation time, what is the relative loss of efficiency, right, or which models are more efficient. So perhaps sometimes running approximate models could be more efficient and result in sort of better inference than exact models, but in a restricted time. Right, I think this is all I wanted to say. Just to summarize that we can handle quite flexible models, including misspecification, ill-posedness, and non-regularity, different rate of contractions, and then can apply sort of to more complex models, sort of more arbitrary rather than just linearly non-identifiable hierarchical models, and sort of use it for further work. Thank you.